Welcome back to my channel, Odavig Structural Hub. This is the #1 channel for structural insight and a place where you learn, build, and innovate. This is day number 5 of revision series, and as you can see, the question is on the board. So we are supposed to analyze this continuous beam using moment distribution method, and henceforth draw the shear force and bending moment diagram indicating all values at critical points. So the question is from past paper and it carries 20 marks. And before I begin tackling the question, let me tell those who have not subscribed to the channel to take a moment and subscribe to the channel and turn on the notification bell so that you may be the first person to be notified when I upload a video. So stay tuned as I start up to the end. Back to the question. As you can see, this is a continuous beam. And a continuous beam is a beam which is resting on more than 2 supports. As you can see, you have support A, B, C, and D. So those are 4 supports, and therefore a continuous beam. So at support A, it is fixed, and at support D, it is fixed. And the loading are point load and UDL, which include 10 kilonewton, which is a point load, placed at 2 meters from support A and 2 meters from support B. So it is at the center of span AB. And then we have a uniformly distributed load of 3 kilonewton per meter, spanning from A to C. And then we have another 10 kilonewton. This is a point load placed at 3 meters from point C and 2 meters from point B. So let's see how we can analyze this continuous beam. So solution. So we'll begin by fixed end moments, like that. So we'll begin by span AB. So for span AB, we'll assume it is fixed at both ends, like this. And then this is the point load of 10 kilonewton and a UDL of 3 kilonewton per meter. Like that. And then we have 2 meters, 2 meters, 2 meters. So we introduce moment at this point as well at this point. So this is point A, this is point B. So this one will be fixed end moment BA, and this one will be fixed end moment AB, like that. So we'll start by saying fixed end moment AB is equal to, as you can see, this one is in the anti-clockwise direction. So we'll start by writing the formula for the point load, which is minus WL all over 8, because this point load is at the center, and this is the formula for that. And then we come to UDL minus WL square all over 12. So that is a formula for a UDL. So this one is equal to minus 10 times L is 2 plus 2, that is 4, all over 8. Then minus 3 times 4 square all over 12. So this one is equal to minus 10 times 4 all over 8 minus 3 times 4 square all over 12. So this is minus 9 kilonewton meter. So that is fixed end moment AB. Then we proceed to fixed end moment BA. So for BA, as you can see, BA is moving in clockwise direction. So this one would be plus. We start with a point load plus WL all over 8 plus WL square all over 12. So this is for UDL. So this one is equal to 10 times 4 all over 8 plus 3 times 4 square all over 12. So this one is equal to 10 times 4 all over 8 plus 3 times 4 square all over 12. So this is positive 9 kilonewton meter. So write this somewhere because we'll use them in the distribution table. So we proceed. So I want to say something, and this is about the portal frame. For example, in case you are given a portal frame like this one, like this one, and then it has a combination of both point load and UDL, like that. So this is A, B, C, D. So for span BC, to calculate fixed end moment, the approach is the same as we have done on this AB. So the approach is the same. So don't panic. Use the same principle, whereby fixed end moment, for example, BC. So this is BC, fixed end moment BC, and this one is fixed end moment CB. So fixed end moment BC will be given by W negative WL all over 8 minus WL square all over 12. So the approach is the same. When it comes to fixed end moment CB, because this moment is moving in clockwise direction, so this one will be plus plus. So the approach remains the same. We proceed to span BC. So for span BC, we assume both ends are fixed, like that, and then we introduce our UDL here, which is 3 kilonewton per meter. Then this is B, this is C, and this is 4 meters. So this will be moment fixed end, moment CB, and this one will be fixed end moment BC. So we'll start by fixed end moment BC, which will be in the anti-clockwise direction. So the formula will be minus WL square all over 12. So this one is equal to minus 3 times L4 square all over 12. So this one is equal to minus 3 times 4 square all over 12. So it's negative 4 kilonewton meter. And then you proceed to fixed end moment CB. CB, as you can see, is moving in clockwise direction. Therefore, the formula will change to plus WL square all over 12. So this one is equal to 3 times 4 square all over 12, which will give us positive 4 kilonewton meter. So we are done with span BC. We proceed to span CD. Span CD. So for span CD, we assume the end support are fixed. Then you have a loading here of a point load of 10 kilonewton. This is C, this is D. The dimension are 3 meters, 2 meters. So we introduce fixed end moment BC. Fixed end moment CB. So we'll start by fixed end moment CB, which is in the anti-clockwise direction, and the formula will be minus WAB square all over 12. So this one is equal to minus 10 times A. A is from here to here, which is 3, times B, which is here from here to here. So 2 square all over 5 square. So this one will be negative 10 times 3 times 2 square all over 25. So it's negative 4.8 kilonewton meter. And then we proceed to fixed end moment DC. So this one will be, this moment is in clockwise direction, and therefore plus WA square B over L square. So this one is equal to 10 times 3 square times 2 all over 5 square. So this one is equal to 10 times 3 square times 2 all over 5 square. So it's 7.2 kilonewton meter. So we are done with fixed end moments, and we proceed to stiffness factors. stiffness factors. Which is K. So we'll start by KAB for span AB. So KAB, as you can see, span AB, the farthest joint, which is A, is fixed, and therefore the formula for KAB will be I over L, or 4 EI all over L. So I want to use the both I over L or 4 EI over L. So in your exam, you will choose the one which will save your time. So I over L is equal to, which is equal to I over L is equal to I is 2, and L is 4. So this one is equal to a half, and 4, which imply 4 EI over L is equal to 4. E is constant, so I is 2 all over L. L is 4. So this one is equal to 2 because this will cancel with this one. So that is it. We proceed to KBC. KBC, as you can see, a span BC, the farthest joint, which is C, is a continuous joint, and therefore the formula remains the same. I over L, or 4 EI all over L. So for I, which imply I over L is equal to, as you can see, I here is 1 and L is 4. So 1 over 4. And for 4 EI over L is equal to 4, E here is constant, times I is 1 all over L. L is 4. So this one is equal to 1. And then we proceed to KCD. So as you can see, for CD, the farthest joint is D, which is fixed. So the formula remains the same. I over L, or 4 EI all over L. So this one is equal to I is 2 and L is 5. So this is for, which imply I over L is equal to 2 over 5. And then for 4 EI over L is equal to, that is 4, E is constant, times 2 all over 5, which is L. So this one is equal to 8 over 5. 8 over 5. So you can write this somewhere because we are going to use them in distribution factors. So let me write them here. So we have I, KAB, for I over L is equal to a half, and 4 EI over L is equal to 2, like that. Then we proceed to K, BC. I over L is equal to 1 over 4. Then 4 EI over L is equal to 1. Then you proceed to KCD. So this one is equal to I over L is equal to 2 over 5 and 4 EI over L is equal to 8 over 5, like that. And then you proceed to distribution factors. So in your exam, you will choose the method which will save your time. So distribution factors. So we start by joint A. As you can see, joint A, it has KAB. No, distribution factor AB, which is equal to 0 because it is fixed. And then we proceed to joint B. So for joint B, we have distribution factor BA, which will be given by this formula KBA or KAB all over KAB plus KBC. So if we use I over L, it will be a half all over a half plus a quarter. So this one will give us a half all over a half plus 1 over 4. So we'll get 0.6, or let's use the fraction. This is 2 over 3. In fact, fraction is the best, 2 over 3. And if we decide to use this one, 4 EI over L, we will get this one, that is 2 all over 2 plus 1. So you get the similar answer, 2 over 3, like that. And then we proceed to distribution factor BC. So for BC, DFBC is equal to KBC all over KBC plus KBA. So this one is equal to, if we use I over L, KBC is 1 over 4 over 1 over 4 plus KBA or KAB is a half. So this one is equal to 1 over 3. And remember, the total distribution factor at a joint, at a pinned joint or a simple joint, it must give you 1. So take 2 over 3 plus a third. So it gives you 1, therefore K. So if again we decide to use 4 EI over L, we have this one, which is 1 all over 1 plus 2, which is equal to 1 over 3. So it is up to you to choose which method will save your time in or during your exam. And then we proceed to joint. This is joint B. We proceed to joint C. So write this somewhere. So let me copy them here. We have DF BA is equal to 2 over 3, and then DF BC is equal to a third. This one is equal to 0. I think you will remember it, so no need to write it. So we proceed to joint C. So for C, we have DF BFCB. So this one will be given by this formula K CB all over KCB plus KCD. So this one is equal to, if we use the I over L, so for KCB or KBC is 1 over 4 all over 1 over 4 plus KCD, that is 2 over 5. So this one will give us 1 over 4 divided by 1 over 4 plus 2 over 5. So it's 5 over 13. Or if we decide to use 4EI, so this one I'm not going to write it here. I just want to punch it direct in our calculator. So KCB is 1. So that is 1 all over 1 plus 8 over 5. You will still get the same under 5 over 13. And then we proceed to DF DFCD. So this one is equal to K CD all over K CD plus K CB. So this one is equal to, we use I over L, 2 over 5 over 2 over 5 plus 1 over 4. So this one is equal to 2 over 5 over 2 over 5 plus 1 over 4. So this is 8 over 13. So the total distribution factor at a joint, it must add up to 1. This is for a simple joint or a pinned joint. So this one, 1, and therefore correct. And if we decide to use 4EI over L, so we'll start by 8 over 5. This is 8 over 5 divided by 8 over 5 plus 1. You get similar under 8 over 13. Then we proceed to what we call joint D. So for joint D, we have DF BC. So this one is equal to 0 because it is fixed, is equal to 0. After here, we can now draw the distribution table and start working on it. Again, allow me to write this here. So we have DF, this is CB, is equal to 5 over 13. And then DF CD is equal to 8 over 13. Like that. DF, this is 0. We'll remember that one, so don't worry. This is the distribution table, and I want to take you through step by step from the top up to the final moments. So we start with the joint. Under joint, we have joint A, joint B, joint C, and joint D. A, B, C, D. And then below joint, you have the member. At joint A, you have member AB. Here it is. And then at B, you have member BA. Here it is. And then member BC. Here it is. And then at joint C, we have member CB and member CD. And then at D, we have member DC. And then below member, we have the distribution factors. And here, for AB is 0. And then BA is here, which is 2 over 3. And then BC is 1 over 3. We proceed to CB. CB is here, 5 over 13. And then CD is 8 over 13. And then for the DC is 0. And then the fixed end moment, we have already calculated this, and we have their values. So for AB is negative 9, BA is positive 9, BC is negative 4, CB is positive 4, CD is negative 4.8, and DC is 7.2. Then from here, as you proceed downwards, now this is our calculation. So I want to explain how I arrived on these figures. So we start by balancing, and what will help you to know if you are supposed to balance and when to carry over and so on. Now, to balance, we only balance a joint which has 2 members and above. We only balance a joint which has 2 members and above. So it can be 2 members, 3 members, etc. So for this case, joint A is fixed and joint D is fixed. So this one will not touch their fixed end moments. But if joint A and joint B were pinned, if these joints are pinned, then it means you have to release them, because a pinned joint, it has 0 moment. So this is a pinned joint. So this one is pinned and this one is pinned. So you will have to release these 2 joints. Releasing, it means you have to find a value which you add or you minus from fixed end moment, then it will give you 0. So that is not for our case. Let's proceed with this one. So joint B and joint C, it has two members. So this is member BA and BC. Therefore, you have to balance joint B and joint C. And to balance, it means if you add the fixed end moment in that joint, it must give you 0 for such a joint to be in balance. But if the answer is not equal to 0, then it means that joint is not balanced, and therefore you have to balance. So for example, joint B, it has member BA and BC. So take 9, add to -4. 9 add to -4, you will get 5. 9 plus -4 is equal to +5. So the joint is not balanced. Therefore, you have to balance. So to balance, this value is positive. So this is +5. So to balance, change the sign here, which is positive, to negative, and the value will remain. So -5. Take this -5 and distribute it equally to each member. So to distribute it means -5 times 2/3. You will get -10/3. And -5 times 1/3, you will get -5/3. And by doing so, you have balanced that joint. And then come to C. Again, do the same. Take 4 plus -4.8. 4 plus -4.8. So what will be the answer? Of course, the answer is not equal to 0. So if you take 4 plus -4.8, you get -4/5. -4/5. So to balance, change this sign to positive. +4/5, and multiply this +4/5 by the distribution factors for each member. So +4/5 times 5/13, you'll get 4/13, and if you take +4/5 times 8/3, you will get 32/65. Yes, we'll get 32/65. And what follows next after balancing? What follows next is carry over. Carry over, you'll take a half. You'll take a half of the member, the value of the member you have balanced, to the next opposite member. For example, member BA, the opposite is AB. So you take a half of 10, -10/3 to AB, which will be -5/3. The same way to B, take a half of -5/3 to CB. It will be -5/6. A half of 4/13 to the opposite member, you will get 2/13. And then a half of CD to the opposite member, which is DC, it will be 16/65. Again, after doing so, you balance. To balance, it means take this value, which is 2/13, change the sign, which is positive. So if you change, the sign will become negative. -2/13, distribute it equally to each of these members. So -2/13 times 2/3, you will get -4/9. -2/13 times a third, you will get -2/9. Repeat the same procedure to this -5/6. So change the sign first. If you change the sign, you will get +5/6 times 5/13. You will get 25/78. +5/6 times 8/13, you'll get 20/39. carry over a half of this to the opposite member. So BA opposite member is AB, and then a half of BC to the opposite member, which is CB, and then a half of CB to the opposite member, which is BC. So a half to this, a half to this, and then a half of CD to DC, this one. Again, balance. To balance, it means change the sign here from positive to negative, and then distribute it equally by multiplying negative 25 over 156 times 2 over 3, you get the value. Negative 25 over 156 times a third, you write your value here. Again, repeat the same procedure to this one. So change this sign to positive. And then positive 1 over 9 times 5 over 13, you will get this one. Positive 1 over 9 times 8 over 13, you will get this one. Carry over half of this to the opposite member, half of this to the opposite member, half of this to the opposite member, half of this to the opposite member. Repeat the procedure until you get something like 0.00 or 0.0 whatever, and then you will come to your final moment. So your final moment for AB, you will start adding from fixed end moment, this one plus this one plus this one plus this one plus this one, you will get negative 11. Positive 9 plus this one plus this one plus this one plus this one, you will get positive 5. Negative 4 plus this one plus this one plus this one plus this one, this one, this one, this one, you will get negative 5. 4 plus this one up to this one, you will get positive 4. Negative 4.8, you add this one, you add this one, you add this one, you add this one, you get negative 4. 7.2, add this one, add this one, add this one, add this one, you get positive 8. So this is our final moments. From there, you can now split this continuous beam into as simple beams. And from there, we can calculate what we call reactions. So let me show you. So AB is negative 11. So this is 11. So no need to indicate the sign because this direction, it will guide you. And then we come to B, at joint B, this is joint B. We have 5. So this one is moving in anti-clockwise, so it will be negative, and this one is moving in clockwise, so it will be positive. So the arrows guides you. And then you come to C. C is here. So C is 4. This one anti-clockwise, negative. This one clockwise, positive. And then you come to D. D. Now this one is moving in clockwise direction, which is 8. So by doing so, I can clean here to create space for continuation. Reactions. We split this continuous beam into simple beams. So this is how we do it. So a common joint like B, we will split it into 2 such that we will have RB1 and RB2. And this one will be RA. And remember the loading here, we have 10 kilonewton and a UDL of 3 kilonewton per meter. Of course, we have the this moment here, which is 5, and we also have a moment here which is 11. So we proceed. Again, C is a common joint. We split it like that. This is a UDL of 3 kilonewton per meter. And remember, we have what we call a moment, which is 5. So this one will be RC1, RC2, like that. And then you have a moment here, which is 4. After that, we proceed to the next joint. So joint D is not a common joint, so it is a single joint, so this is RB. And remember, we have a UDL here, a point load of 10 kilonewton. Again, the moment is here, another moment is here, so this is 8, like that. And the dimension are 3 meters, and this one is 2 meters. For this one is 4 meters, and for this one 2 meters, 2 meters. By doing so, we can easily calculate our reactions. So to calculate reactions, we'll begin by this portion of a simply supported beam. So say summation of moment at RA is equal to 0. So automatically we will be looking for RB1. So RB1 is moving in anti-clockwise direction, and therefore the distance from here up to this point is 2 plus 2, 4. So minus 4 RB1. Then we come to this moment, which is in the anti-clockwise direction, and that one will be minus 11. Then we come to a point load, which is 10 kilonewton. So it is moving in clockwise direction, this way. So plus 10, the distance from here is 2. We'll come to a UDL, which is 3 kilonewton per meter. It is moving in clockwise direction, plus 3 times the distance covered, which is from here to here, that is 4 times 4 over 2, because the moment for UDL, it acts at the center of the distance covered by that UDL. And then we'll come to this moment here, which is 5, and it is moving in clockwise direction, and therefore plus is equal to 0. From there, you can carry out the operation. So this is negative 11 plus 20 plus, this is 12, 12 times 2, 24, and then plus 5. Divide everything by 4. You'll get 9.5. So RB1 is equal to 9.5 kilonewton. So to get RA, you will say summation of upward forces is equal to summation of downward forces, which imply Ra is equal to 10 plus 3 times 4. The total downward forces is 10 plus 3 times 4. 3 is UDL, so you multiply by the distance. Then minus 9.5. So you'll get, this is 10 plus 12 minus 9.5. You'll get 12.5 kilonewton. We proceed to this portion and we'll say summation of moment at RB2 is equal to 0, and therefore negative 4 RC1, because RC1 is moving in anti-clockwise direction and the distance from here to here is 4. Then minus, we come to this 5, minus 5, which is a moment, and then the UDL plus 3 times 4 times 4 all over 2. Then you come to this moment, minus 4 is equal to 0. This moment, which is 4, is moving in clockwise direction, so this is plus, not minus. Plus 4 is equal to 0, which imply RC1 RC1 is equal to negative 5 plus 3 times 4 times 2 plus 4, then divide everything by 4. So this is 5.75 kilonewton. To get RB2, this one will be 3 times 4 minus 5.75. So the reason is summation of upward forces is equal to summation of downward forces. From there you can make an equation and obtain RB2. So this is 12 minus 5.75. So this one is equal to 6.25 kilonewton. We proceed to this portion. So we'll say summation of moment at RC2 is equal to 0. This one will be negative 5 RD, because RD is moving in anti-clockwise direction and the distance from here to here is 3 plus 2, which is 5. Then we come to this we come to this moment which is in the anti-clockwise direction, minus 4. Then we come to a point load plus 10 times 3. So this point load is moving in clockwise direction, and then you come to 8, which is in clockwise direction also, is equal to 0, which imply RD is equal to, we carry out the operation, negative 4 plus 30 plus 8, divide everything by 5. So this is 6.8 kilonewton. Then RC2 will be 10 minus 6.8, which is equal to 3.2 kilonewton. And then we'll come here and say RB is equal to RB1, which is 9.5 plus RB2. Where is RB2? RB2 is here, 6.25. So you get 15.75 kilonewton, and RC is equal to RC1. Here it is, plus RC2. RC2 is here, plus 3.2. So you get 8.95 kilonewton. Then from there, you can now draw the shear force diagram. So this is the baseline for shear force diagram. Above the baseline is positive and below is negative. So we'll start by RA, which is here. RA is 12.5. So it is positive. So we approximate 12.5 somewhere like here. So 12.5. Then take your calculator, write 12.5, then minus UDL. This is 3 times distance from here to here times 2. You'll get 6.5. So 6.5 somewhere like there, 6.5. So join an inclined line like this, and then take 6.5 minus 10. You'll get negative 3.5. Negative 3.5 somewhere like here, 3.5, like that. So negative 3.5 minus UDL from here to here, so minus 3 times 2, which is 6. You'll get negative 9.5 somewhere like here, 9.5, and then an inclined line like that. So take negative 9.5, add RB. RB is here, plus 15.75. You'll get 6.25. So 6.25 here, so this is 6.25. Take 6.25 minus a UDL from here to this point. So that is 3 times 4, that is 12, minus 12. You'll get negative 5.75. So somewhere like here. So this is 5.75. Draw an inclined line like that. Then take negative 5.75, add RC, plus 8.95. You'll get 3.2 somewhere like here, 3.2. So this 3.2 will be constant up to 10. Then minus 10, you'll get negative 6.8. Negative 6.8. 6.8. then it will be constant up to D. So negative 6.8 add RD plus 6.8, you'll get 0. This is 0. So this is minus, plus, minus, plus, minus, plus. Like that. By doing so, we are done with shear force diagram. We proceed to a bending moment diagram. Now, for the bending moment diagram, you can use two approach, but I want to give you the simplest one for exam, and the other one is for when you are practicing structural engineering. So let me start with the one for exam purposes. So for exam purposes, first calculate free span moments. So you begin by span AB. So span AB, as you can see, is a combination of UDL and a point load. So the formula for a point load is W AB over 4. Then for a UDL is plus W L square all over 8. So this one is equal to 10 times 2 times 2 all over 4 plus 3 times 4 square all over 8. So this one is equal to, this is 10 times 4 all over 4 plus 3 times 4 square all over 8. So this one is 16 kilonewton meter. And then we come to span BC. Span BC is equal to WL square all over 8. So this one is equal to 3 times 4 square all over 8, which is equal to 3 times 4 square all over 8. This is 6 kilonewton meter. And then span CD. So this one is equal to WAB all over L. So this one is equal to 10 times 3 times 2 all over 5. So this one is equal to 10 times 3 times 2 all over 5. So this is 12 kilonewton meter. And then from there, you can now draw the free span moment diagram. Now, to draw the free span moment diagram, draw the baseline and draw the free span moment diagram using these values. So the highest is 16, which is span AB. So span AB, it has a combination of both a point load and a UDL, but this will bend in a parabolic shape. Like that. So this is 15, no 16. So this height is 16. Like that. And then we come to this one, span CD is the second highest with 12 kilonewton meter. So it's somewhere like here. This one will be a triangle like this, and then BC is 6. This one will be a curve. So this one is 6, and here is 12. After doing so, you can come and combine this, the final moment we calculated earlier. So at A is 11, so 11 is below this one. Here is 11, and then at B we have 5. 5 is here, and then here we have 4, and here you have 8, and then you join. So you join like this. So this one is negative, this one is positive, this one is negative, this one is negative, this one is positive, this one is positive, this one is negative. So that is the first approach, the best for exam, because it will save your time. Identify this point and extend this line like that. So this one, we call this distance x, and here 4 minus x. Now to determine x, use similar triangle rule to get this x. So from here to here is 6.25 all over, from here to here x, which is equal to, from here to here, 5.75 all over, from here to here, 4 minus x, which imply x is equal to, cross multiply, x will be 6.25 times 4 divided by 5.75 plus 6.25. So this is 2.08, let's say 1 meters. So here is 2.1, and then 4 minus 2.1 will be 1.9. So to draw the bending moment diagram using shear force diagram is as follows. Now this second approach, draw the baseline and call it BMD, or bending moment diagram, and therefore come here and say bending moment value, or bending moment value at A is equal to negative 11 kilonewton meter. Then bending moment value at this point at this line where 10 kilonewton is acting. Let's call it Y or Z. At Z will be negative 11 plus the area of this shaded region plus a half A plus B, because this is a trapezium. So sum of two parallel sides is 12.5 plus 6.5, then times H. H is from here to here, this is 2. So this will give us 12.5 plus 6.5, then times 2 times 0.5. So this is 19. Then negative 11 plus 19. You get 8 kilonewton meter. 8 kilonewton meter. Then we proceed to bending moment value at B. At B, we know at B is 5, but let's prove it. So it will be 8 minus this area, which is a half, into bracket the sum of two parallel sides, 3.5 plus 9.5, then times 2. So this one is equal to, let's prove it, 3.5 plus 9.5 times 2 times 0.5, that is 13. Then 8 minus 13 is negative 5, which is very correct. Then we proceed to bending moment at this point. We call it Y. Bending moment value at Y. So this will be negative 5, then plus a half base times height, a half times 6.5 times from here to here 2.1. So this one is equal to negative 5 plus 0.5 times 6.5 times 2.1. You get 1.8 kilonewton meter. A bending moment value at C, we know at C is 4, but let's prove it. So this one will be 1.8 minus this area minus a half times 5.75 times from here to here is 1.9. So this one is equal to 1.8 minus 0.5 times 5.75 times 1.9. So this is negative 4 kilonewton meter. And then bending moment we are at C. Bending moment at where we have 10 kilonewton, you will take negative 4, then plus this area, which is from here to here, is 3.2 times from here to here is 3. So this one is equal to negative 4 plus 3.2 times 3. You'll get 5.6 kilonewton meter. So this is bending moment at this point. And then bending moment at D, we know is 8. So let's prove it. So at D, it will be 5.6 minus this area, which is 6.8 times 2. So 5.6 minus 6.8 times 2. You get minus 8 kilonewton meter, which is correct. Now let's now draw the BM diagram. So we'll start at A. At A we have negative 11. And remember, above this baseline is negative, below is positive. So negative 11, somewhere like here, like that. And then you come to bending moment at Z. At Z, at this point, where 10 kilonewton is, which is, where is the answer? Here it is. Now bending moment at A, bending moment at A is this one, then at Z is this one. So 8, which is positive. Somewhere like here, 8. And then you come to bending moment at B, negative 5. B is here, which is 5. And then at Y, 1.8. This is Y, 1.8. And then at C, negative 4. At C, you have negative 4. This is 4. And then at 10 kilonewton, we have 5.6. And then at D, 8. At D we have 8. So we'll join the dots. So this one will be a parabolic curve. Parabolic curve. From here is an inclined line, and then an inclined line. So this is negative, this is positive, this one is negative, this one is positive, this one is positive, this one is negative, this one is negative. And by doing so, you have come up with a bending moment diagram. So the second option, or the second approach, is very best when doing the real thing or doing the real design. But for the first approach is best for exam purposes. So that one marks for the end of that question, and the revision series is still on up to the end of this week. So stay tuned for more. And for those who have not subscribed to the channel, please subscribe and turn on the notification bell so that you may be the first person to be notified when I upload a video. Thank you for your time, and we meet again in my next session.